No, testing. Okay. Okay, so let's talk a little bit about difference between subbases and bases before we start. Okay, so for examples, let's take an examples. So if you consider basis elements of all the open balls, in R2. Okay, yesterday we showed that this is a basis. Yeah, and then the topology generated by this basis is actually the Euclidean topology. Okay. But if you consider subbases, what does it mean? You are taking union of finite intersection of these four. Okay, meaning what? What kind of thing is inside your topology? So for example, this kind of intersection. Okay, for example, this intersection okay, of the two open ball is actually open, okay, in the topology generated by the subbasis B. Okay. Previously, if I take this as a basis element, then what do we do? What do we need to do? We need to show that for every two intersection, we need to be able to find another open ball. But in subbasis, then we already declare this non-open ball like region to be open already. Okay, now. Also, okay. So there's more open set inside the sub basis topology. And if you generate using the same set of elements. Okay, no. That's the last proposition we had last lecture. Okay, so the the topology generated by subbasis B is finer than the topology generated by basis B. Okay, it's finer because you have more. Does it make sense? Okay, no. So subbases, you need to consider finite intersection to be open. So meaning this kind of region, you also call it open. Yes. Which alphabet? For beta. So the difference here is base, subbases, and bases. It's the same set of element you use. Ingredient is the same. Just the method of generate topology is different. Okay, no? Method is, ingredient could be the same. Okay, just the way of generating topology is different. Okay, when we say generated by bases, generated by subbases, okay, the recipe is different. Okay, so what's the basis recipe? You just take union, arbitrary union. But what's the recipe for subbases? Union of finite intersection. Obviously, you include the usual union, right or not? Usual union is okay, but you have more union of finite intersection also included. Okay, no? Can differentiate between bases and subbases now. Okay, for bases you just take union, basis element, but subbases you need to take union of finite intersection. Okay, 明白吗？ Union of finite intersection, you have more. Okay, you have more. Does it make sense? Okay. Any question? No question? No. For example, I give you an example. Last time we talked about rectangle, right? Open rectangle also generate the Euclidean basis, Euclidean topology. Let's say we generate sub-basis using open rectangle. Is it the same topology generated as the basis or not? If we use the open rectangle, so replace this B with open rectangle here. So question here is, so let rectangle. So let R be all the open rectangle. So open rectangle in R2. Okay. So let R be open. So the question is the topology, okay, let's say this is TB, generated by bases are the same topology ESB generated by sub-bases, SUBB, sub-bases are they the same or not? Okay, generate a basis means what? We proved already. The topology have to be the union of all the open rectangle. Generated as sub-basis, union of finite intersection of open rectangle. But yesterday I showed you, right? Intersection of a rectangle should be again a rectangle. They should be the same topology in this case. Okay, no. Okay. Okay, it should be the same. Yeah, should be the same. So answer is should be the same. Okay, so T B, so TXB since intersection finite intersection of open rectangle is still an open. Okay, so you can create all the open set in the other topology. Okay. Any question so far? So basis and sub-basis. If no question, we will continue. Okay, so continue define something called the subspace topology here. And subspace topology. So let S, okay, let S tau be a topological space. If Y is a subset of X, then how do we see open set in Y? Then the collection tau Y here is what? Y intersect U such that U is in the open set of X. Open set in X. Okay, you should prove that this is indeed a topology. And this is what we call the subspace topology. In a moment, I'll give you an example. Okay. So in this case here, with this topology, Y is called a subspace of X. Subspace. So this is not a vector subspace. Okay, be careful. This is not a vector subspace. So when we call set, okay, how to say? Yeah, a set actually. We don't know whether it's a topology yet, but with this topology, this tau Y here, we will make Y into a topological space. And then this topological space is a subspace of X. Okay, we'll call it subspace of X. Okay, why? Because how do you declare something in Y to be open? It really depends on the open set in X. It's really depending on open set in X. Okay. As long as the thing, as long as the subset of Y, they can be written as Y in the set U, it will be open. Okay, I'll give you an example in a moment. Okay, so this subspace is a bit different from the vector subspace. So in other words, its open set consists of all intersection. Okay, all intersection of open set of X with Y. Okay. Let me give you an example. So for example, let's look at some subspace here. So let's consider this half open guy in R. Okay. So usually when we didn't write anything about R, right, usually we will assume R to be with the Euclidean topology. Because yesterday I produced different topology on R, right? The lower limit, the K topology, right? Okay. So if I didn't write specify any topology, it's just a Euclidean topology. Okay. So if you look at this half open interval here, right? Is it open or not? Actually, it's not open, right? Okay, in the Euclidean topology, it's not open. But we will say that as the half open interval can be written as itself intersect, okay, with some open set in R, we will say that this open set here is actually open in itself. Okay, so here we will say that as a subspace topology. Okay, but at the same time, you need to note that this half open interval here is not open, okay, in R with Euclidean topology. Okay, does it make sense? Okay. Well, I mean, can you give another open set inside the half open interval or not? 0 to 1. You try? You want to try? Right? Try. Half 1. Oh, okay. So close, open from half to 1 is open in 0 to 1. Why? You need to write it as what? Y, the subspace, intersect with some open set in R. Can you write it as that or not? Can you write it as 0, 1 intersect with some open set or not? Yeah, just take the open interval in R going from half to 1. Okay. Okay. Okay, make sense? Okay. Okay. So you can see that with subspace topology, right? We will declare that this kind of non-open thing in R to be open. Right? This is one of the benefits. Okay, where we look into just want to look at some subspace. Okay. Does that make sense? Actually, it's not open, right? This guy in R is not open. Okay. But we need to be careful whether we are using subspace topology or the ambient topology. So in the question, right, usually when we want to use subspace topology, will tell you as a subspace topology. Okay, in subspace topology. Or we will use this kind of terminology, open in where. Okay. If open in some subspace, then we will say that we will use it as a subspace topology. Okay. Okay, so be careful. Don't confuse. Please don't confuse. Okay. Yeah. So one thing you can show is what's the basis? What do you think? What's the basis for this subspace topology here? Yeah. Let's say we know that we have a basis for the topology of X. Okay. If you have a basis for topology of X, then what do you think is a basis for your subspace topology? What do you think? Huh? What do you think? How do you make your subspace topology? You use what? What operation you take for subspace topology? Y intersect with open set in X. Okay. So basis left, what do you think? An obvious construction you can think of. Huh? Must be have something to do with the basis element of B. Then you want this B to stay inside Y. There's one construction you can do. You just take the intersection. Okay, just take intersection. Okay, the claim is this is a basis for the subspace topology. Okay, subspace topology. Okay, no. Okay. Okay, I'll leave you to prove this yourself. Okay, next. Before we leave the subspace stuff, next is I think this one is quite interesting. So let Y be a subspace of X. So meaning you inherit the topology as a subspace topology. So the claim is if U is open in Y and very important, you need this condition, and Y is open in X, only then this openness is transitive. Okay, make sense? If U is open in Y and Y is open in X, then U is open in X. Just now I gave you that example already, right? You see, the half closed interval is open in itself, but it's not open in R. Then the whole thing is not open in R. Okay, but if you know that, if U is open in Y and at the same time Y is open in X, then Y is open in U is open in X. Okay, now you see, the first two conditions that doesn't talk about U open in X. You only know U in Y, and then you know Y in X. Then you will know about how U sit in X. Okay, got picture inside your mind. So you got a U, okay, in X, or U in Y, but Y is open in X. Okay, then you will see that this U here is open in. Okay. Okay, let's see how we prove this. Okay, let's see how I prove this. Pretty straightforward here. Okay, so like what I told you, we are not really constructive in our topological proof. You just use definition. Just use the definition. So since U is open in Y, okay, since U is open in Y, what does it mean? As a subspace topology, this means what? There exists some open set in V, right? Some open set V in X such that U equals to Y intercept V. Okay, this is the first openness. But what? You see, you write U as intersection of Y and U, right? And V, sorry. But at the same time, what's the condition on Y? Assumption on Y. Y is open in X. Where you take the V from? V is open, is also open in X. So the intersection of two open set is open. Okay or not? So since y v are open x, so so u as a finite intersection of open set is open in x. Okay, no? Okay, very straightforward. Okay. So far what we have did is we introduced topological space, and we introduced how to uh, find basis for this topological space. Okay, and then we proved that actually if you have a basis, your topology is just union of this basis element. So that's why we call it basis, no? Because all the open set is just union of these basis elements. Okay, and then what do we do? We so topology become basis, and then if I gave you uh what did we show last time? What's the other direction again? So I give you a topology. No, we start with a basis, then we can define a topology. If I give you a topology, how to find the basis? What's the criteria? The condition on C, right? The script C condition. Do you remember the script C condition? Okay. And then what's the next thing we do after that? We define subbasis. Here we define subbasis. Okay, so which is the union of finite intersection. Okay. Okay. So in this case, means what? Finite intersection become your basis. And finite intersection of subbases become your basis. Okay. And then we define the subspace topology. Okay, so this is about topology for now. Open topology. Okay, any questions? Okay, so these are about open topology. So now we will move on to closed topology. Okay, so before we can define closed topology, we need to tell you what are the closed set first. Okay, and maybe together with a limit point. So the treatment is exactly the same how we did for matrix spaces. In matrix spaces, I tell you what are the open ball first. Okay, what's that open? Okay, I tell you what is closed just by the complement of open set. Okay, so it's the same treatment here. Okay, parallel treatment here. So we'll define closed set here. So what do you think? What do you think? How do we define a set is closed in a topology? Sorry? Not open. What's But we haven't defined not open yet, right? Okay, so we need to use something that are defined. We define something to be open, right? Okay, so can you use openness to define close? How do we define close last time? Close set. I think I asked Ivan last time. Let's ask Ivan again. What's a close set means? 什么？不要笑，不要笑。What's a close set mean? A set is closed in what? Huh? A set is closed in what? 精神偷偷跟他讲什么叫做 complement is open？complement 是什么？对，非常好，AC 对，OK，它的外面是 open。So in this case here, where is the complement? If X take away A is open. Okay, so we use something that we know to show that to prove to define new things. Do you know open or not? Which letter tells you I know open? Hey, which letter inside this sentence here tell you I know what is open? Which letter? Or which symbol? No. I'm referring to the open property here. How do I know something is open? What is the thing that helps me to check some set is open? No, no, you circling already, circling. So open here, you need to check from tau. Tau is a collection of things that tells you what are open. So you need to ask yourself whether x minus a is inside tau or not. This sentence means. Okay, so maybe it be super clear here. So that is whether x minus a live inside tau or not. Okay, because tau is the collection of open set. Okay, so meaning a set is closed if x minus a is in tau. Okay, make sense? Okay. All right. Yeah. Okay. I think we have a lot of examples. Nice example here. Okay, so let's do some warm-up example first. So for example, closed interval. We say it is closed. Maybe in the high school, you will just think that, oh, because I take the endpoint, so it is closed. Okay. But now, can you write it as a complement? Okay, can you check its complement or not? What is it complement? What's the complement of this closed interval here? I want to try. What's the complement of this closed interval? Then, okay. Union to infinity. Okay. So yesterday we see that these two are open set, but you are just union two open set together. So it's again open. Okay, because the complement is open. Okay, maybe you think that I cheat a bit. I cheat a bit. What way did I cheat? Why this infinity guy is open? Why? Why? Why this infinity guy is open? Union of open set. Okay, so can you write it as a union of some open set or not? Such that your left endpoint will go to negative infinity. I from I to A like that. Huh? A minus 1 to A and then? Okay, A minus I to A and then we take I to from 1 to infinity. It works. Okay, yeah. So dot. Sure, I know what are you dotting. Okay, wait, let me draw it. Okay, wait. I get what you mean. Wait, before let me write down the other one first. Okay, so what is he's trying to do, So you take A, okay, and then A minus 1, and then A minus 2, and then keep going. Okay, and then you take the union of all these open. Okay, makes sense, This is not the only way you can write yourself. Put 2i also can. That's one. Yeah. As long as it's growing to the negative infinity. Okay. But I mean, because arbitrary union of open set is still open, right? Open is open. So it's okay. So here is an infinite union. Okay. The other one, I'll link to my other course. The other one is algebraic geometry. Okay, so anyone that took that course know what I'm going to talk next. What's the closed set? What's the closed set here? I think we introduced RSK topology last week. So what's the closed set there? Find algebraic set. So what's R5 algebraic set? Zeros of, let's just talk about one polynomial. So zeros of n polynomial. So what do we mean by zeros of polynomials? So for example, all the xy such that y equals to x squared. Okay, what's this? In picture as a graph. What's this graph? This is the parabola. Y equals to x squared. Okay, but what's the union? What's the complement here? Anything that is not on this line here, this parabola. So how do you write it? So r squared take away this closed set here is equals to all the point xy such that y is strictly less than x squared union xy such that y is strictly greater than x squared. Okay, and then this two set is open. Hey, this two set y is open now. You can check in the Euclidean topology or the metric space. Why open? How to show something is open inside a metric space? You take any point on this complement, show that there's an open ball. Can you do that or not? Can you do that? Are you able to do that? If I give you any point, let's say 很靠近这条线，还可以找到 open ball 嘛？应该要放大一点了，要放大一点。So can you find an open ball to avoid this parabola? Okay. I think the shorter distance is this distance, I guess. I'm not sure how to find it, but this is should be the shortest distance. Is it? Do you know the 90 degree or not? I'm not sure. Because this is the one perpendicular. Yeah, right. Perpendicular, but you see your thing is not straight also, right? So really a bit hard to say that. But I mean, can you convince yourself that we can find an open ball around this that avoid parabola curve here? No matter how close I gave you, you still can find an open ball. Yeah. Okay, let's say what's the yeah, sure. Yes. So the problem is how you get the closest distance. How you define that closest distance. I mean, one way to define is like in your assignment, right? Infimum of d of x with all the point in the parabola. Your E is the parabola in this case. Infimum. And then you need to show that your infimum has to be strictly greater than 0. So once you show that infimum of the xy is strictly greater than 0, then you can form this ball already. Make sense? Okay. Okay, cool. So if you consider these zeros of polynomials, right, they form the topology also, okay, which we call Zariski topology. But later we will see what do we see. Okay, I think. Okay, and then maybe another really close example also to algebraic geometry. So let us ask about closed set in the finite complement topology. And we will record for you what finite complement means. Well, finite complement, this word already suggesting you the definition. Finite complement, meaning what? The complement is a finite set. Okay, so let's write it out. What's a closed set here means? So if C is closed in X, by definition, the complement is open. But let's recall what does it mean by open in this finite complement means? What does it mean? So it means that there are two things you need to check, right? Either the complement of this guy, okay, is finite, or the complement of this guy is the whole set. Okay? Remember last time we include this so that we can include the empty set into our topology. But this implies what? This just implies that our closed set must be either finite or the whole space. Okay. So this proves that the closed set in finite complement topology is either finite set or the whole space. Okay. Sorry. 少了啥？哦，谢谢。equal 哈，OK。closed set。Okay. Yeah. So in particular, last time in the AG class also we proved that the closed set inside A1 is either finite set or the whole space. Okay, so if you prove that the Zariski topology that you define on A1 is a finite complement topology, you also prove that the only thing to happen is a finite set and S must be is closed. Okay, the way we prove it last time was using polynomials, right? Yeah, but this one is a topological way to prove it. But obviously, you need to argue that why the Zariski topology is a finite complement topology first. I'm not sure whether that need to include argument or polynomial. Okay, so next, how about discrete topology? What are the closed set in discrete topology? What is the closed set in discrete topology? So C has to be closed in X if X minus C is open in the X. So meaning what? Your discrete topology is just what? What's your discrete topology? I still remember or not? What's your basis? Basis is the singleton, right? So the whole topology is just your power set. But if you take any set or any subset inside of X, X minus that subset is still a subset of the X. So it's always live inside PX. So in discrete topology, every subset of X is closed. Actually, they are at the same time closed and open. 有没有颠覆三观 ？Okay. So actually, every subset C is closed in X. Of X is closed in X. Okay, because if you take it away, the complement is still a subset of X, which is an element of your power set that is open. Okay, so it's at the same time closed and open. Okay, everything, every subset inside your discrete topology of X. Okay. So similarly, you can prove that. Okay, so similarly, we will prove that let X tilde Xt be a topological space. Okay. Then we'll see that the whole space and X are closed. Okay, why? Can you write them as a complement of something else or not? Phi equals to what? X take away what? Itself. But itself is open, right? Okay. Let me see. Am I saying the right thing? So yeah. So because x minus x is also open, you write it as a complement, and then this is element in tau because empty set is open. Okay. How about x? Can you write it as a complement of something or not? Huh? Complement of empty. Okay, but this complement here is again living in tau. So what I demonstrate to you is within a topological space, there's at least two things is both open and both closed. One is empty set, the other one is whole space. Second, arbitrary intersection of closed set are closed. Okay. Hey, by the way, sorry, the first statement here is telling you that X is closed, and then the second statement here telling you that phi is closed. Okay, because we are looking at the complement of X for the first one. The second one is looking at the complement of P. Okay, so please don't confuse them. Okay, no? Okay. So next, we want to check arbitrary intersection of closed set. So let's write down the arbitrary intersection of closed set. So we need to look at the complement of this guy. Is it open or not? What's the complement of this guy? X take away some intersection becomes what? How complement react with intersection? Like a De Morgan's law, right? Okay, so you become a union of complement. Okay, but what do we know about CI? CI are closed. So the complement is open. But this is an arbitrary union of open set, which is open. Okay. So it's a very nice complement relation between closed set and open set. Guess the last property or not? The last property. We talked about arbitrary already, right? Finite union, good. Finite union of closed set are closed. So you need to check the what? The complement of this finite union here. What does it become? Intersection of x take away c, which is open. Okay. So what you can see here, you see, all this argument here is just coming from first week, second week on set theory. Okay, how complement react with union and intersection. Okay. So that's why I asked you to prove it in the first week. So now we are using it already. Make sense? Then we check that how is it inside some special set that we consider. Even when we consider this special set, we still use union and intersection property to define it. Okay, so everything is just set theory here. Okay. 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 Okay, so the remark here is instead of using open set, right, one could just specify a topology on a space given a collection of closed set. Okay, and then we will just define open set as a complement of closed sets. Okay, so I think Lydia last time asked the question of inside a set, right? You have a topology. The number of closed set and number of open set is the same or not? Do you think it's the same or not? Of course, the same. Why? So yeah, so the bijection there, the bijection is just the taking complement. Okay, so taking complement is a bijective action. Yeah, it's unique, right? Should be unique, right? The complement of me is just everything else. and then the congruence of everything else is just shouldn't be something else. Should be unique. Okay, so it's a bijection. Complement is a bijection. Okay, so similarly, you can define subspace topology for closed topology. Okay. Should we do this? Oh, this one is quite interesting, huh? Okay, let's do this lah. I think something to play with here. Okay, let's define subspace topology for closed topology also. So if Y is a subspace of X, we say that a set A is closed in Y if A is a subset of Y and A is closed in the subspace topology of Y. Okay, that is Y minus A is opened in Y. Okay, I want you to note some terminology here. When we say open in Y here, this is as a subspace topology, right? We never say that Y minus A is an open subset of Y. We don't use this notation. I'm not sure if any book uses that, but maybe some lecturer here will use it. So I want you to distinguish it. So be careful when people talk about it. But in this class, we will only talk about open in a subspace. Only this condition you will use subspace topology. Okay. Okay. No. Okay. Open in some subspace. We didn't use open subset of something. We didn't define that also. Okay. Yeah. So just open in a subspace. Or I will specifically mention you that we are using subspace topology. Okay. Okay, then the next lemma is, so this is a closed subspace topology here. So the next lemma is we're gonna reformulate this definition similar to what we had in the open subspace topology. Okay, what's the open subspace topology here? Sorry, closed subspace topology. What do you think? If I want to formulate a similar one with the open subspace topology. Remember how we form the open subspace topology? As long as your set can be written as a intersection of the subspace and with what? With open set in the original space. Cannot recall. Yeah. Okay. You want to write all your open set in your subspace as an intersection of the subspace with the open set in the original space. Okay. So in this case here, when we define closed subspace topology, right, we didn't write this. Okay, we didn't write it. But we're gonna formulate that it is also the same as saying that this A is the intersection of C and Y such that C is closed X. Okay, so we're gonna prove this. We will do it together later, and there's a very nice picture to see for this proof. Okay. Okay. So in fact, these two definitions are equivalent. Okay. Okay, any question before we break? Later we'll prove this. Okay, let's break until 4:03. Oh, okay.
不用
啊？
我说我刚刚在说的是这个第4题，好像不用 algebra close。因为你看我们上课的时候 prove 过这么一个东西，你还记得吗？那么你看这道题的条件，如果直接用这个莱玛的话 ，A 是 zero 的，对不对？然后它是
怎么我 feel 了 you over feel， 我有答错吗？
哪里？你要看到它用它吗？下面它在这里。
哦，if over a few 是这个的 feel，OK。
那你看，如果我们用这个东西，首先它自己是一个，它自己是不是一个 affine domain？
他自己
对
，OK，A 自己
所以 A contain 在它自己里面是显然的。
，OK。
然后再加上 A 自己是 field，都出现了 A 是 algebraic。
哦，你是说你要用这个 lemma 是吗？
对，我用这个莱玛其实直接得出来了。问题是这个莱玛并不要求 K 是 algebraic closed。所以我觉得实际上这个 algebraic closed 可能不需要。虽然我觉得你把它设成一个 assignment 的目的肯定不是让我们直接用这个 lemma。
对，因为 OK，其实我是在重新证那一个东西，是重新就是靠着这3个东西重新证这句。
这句话你是要用前3个东西来证。
不然怎么会在一起？
对
呀，不然他们干嘛在一起？
因为那3需要1和2吗
3需要1和2吗？好像是要，好像是要。但是如果你没有经过1和2也不用紧，但是肯定都讲这句话跟那句话差不多是一模一样，所以就来。
问题是我去看3的时候，网上基本上就没有一个比较能直接读懂的证明。
肯定这些东西是在某一个课本里面，那本 Cloud 里面。对，其实就是 mouse read 的东西啊，但是 Cloud 写的比较完整。
怎么
我放在那个 就 V 级的那边里面，我不是在班上有讲吗？
没听到的音？
对啊，你开一下目的。
第2题还是比较好做。
OK。
没有，我说第2题是第2大题，就那个什么莱玛来着？那个那还亚马莱玛。怎么这个课上那么多日本人啊？
很厉害呀。
好吧。
确实给你讲一下，我才发现好像很厉害的人都是日本人。
对呀，是不是？
不奇怪。对耶，他课本也是很完整啊。日本的话，课本就是 algebra geometry 的课本哦。如果你去日本玩的话，
你猜那篇大概金妈的 Hilbert scheme， 我们第一页有多读不懂？
我们俩联系3个以前谈的。project 还是咱们
2个
自信一点，把一点去掉。
OK。
让我们争
呀。下次我给你多一点 hint 啊。OK， 我下次给你多一点 hint。
但是我看了3好像没有3分之2难，我目前瞄了一眼来看，
还是没有。
哪个？
麻烦在哪里呀？
可以 extend 吗？
可以，你要 extend 多久？
我不懂。
那个 sorry，
你这个你要安排一下。这个你要安排一下。我可以 extend，但是
我很认真讲哦。
可以。
我听不懂哎。
不用紧啊，我上课的时候也没有听得懂我老师讲，但是我还是把答案交了，就是老实话回复你。这个
model 啊，挺有水平。
而且我可以告诉你啊，3门2的答案是可以在那个课本里面有。这样这个你要花时间看，这个没有办法，这没有办法。这个办法就是要花时间。Well， 对，可能对，我们只能够努力干就完了，因为你哭也不是，但是我没有，我明白，我给你看，你哭是 OK，你看你要 acknowledge 你自己的决定，你读读看。 那你对，那你就是对的。OK，他是对的啊。然后他写什么？他是对的，三星也是对的。但是你要知道你是拥有备胎。Scare 也 OK 啊，因为是你身体要保护，是 OK 的。也可以生气啊，没问题。但是休息很重要。
对，
真的，我跟你讲，这个是幼稚园，这是澳洲幼稚园教澳洲学生做的事情。这样，是这样啊。我也笨了几年，其实。是我可以告诉你的，就是你会活得跟很多人不一样，就这样。嗯believe the process，相信的 process，过得来的，过得来，我可以 extend 你啊，但是你要决定一下，安排一下。
对，拜五，
中
拜五很不方便诶。
要放
你放我每天的时间，
每个时间？
每天就是那个
就
时间
拜二之间。OK
都
OK，
定好了，不要
OK
不要
没有，因为那时候我是 like，因为我本来要定，你知道为什么拜五吗？如果我定这个拜二是更快，你知道吗？所以我才放到拜五，你知道吗？
所以
本来我是放这个拜二，因为是隔一个礼拜嘛，所以我才放到拜五去啊。
哇，testament 我没上你的课为苦。
是，
哇，我觉得我尽可能做了完。
可以，尽力了。那不能我再看啊，看有没有程度在哪里啊，我也是不知道。耶，嗯，耶，是不是？呀，我觉得你相信那个 process，你会不一样。
你问这个问题，
不会 destroy 你啊，不会可能。可以，你不用怕，可以。
这 topology basis 上，我可以想成来 minimal set of open set that generate 整个 topology。
但是我昨天就跟你讲了嘛，它不一定是 minimum 嘛。
就是其实我还想知道，我拿全部 basis as singleton 啊，它可以 generate any topology in。
可能啊，它 generate 不同的 topology，我可以给你看。它 generate topology 叫做 discrete topology，
所以它就是所以它
它可能会包含其他 topology，但是它肯定不是其他的 topology，
像我
它是
basis，
个 finest topology。
所以我 basis 就好像你那就不要这样，我不能拿多，不能拿少。我一拿多，它是不同 space
啊，有可能会变不同，
我拿少，它又不同的，
可能有不同，会不同。
可能
但是重点就是跟 vector space 的一个共同性，就是你可以 express 你的 open set as union of bases。
对的。
然后你 vector space 是写成 linear combination of bases。
就是上 basis 是什么意思先？
上面就是它 consider 的 open set 是 finite intersection 也 consider 进去，它不止 basis 才能跟它合在一起，它连 finite intersection 的，因为你们刚才词来，我画了一个图，
我懂呀。
你看之前不是告诉你说这个东西不 open 吗？但是如果上 basis 的话，这一个 intersection 就变 open 了哎，它形状都不是 open 过来的。
只是我们的 basis 的条件就是讲，
这本书在哪？
一定要有
啊，你去搜哪开亚吗？雷马，然后28枚，我记得。
就是那个 basis 的那个条件就是讲，如果有两个 intersection 的 basis 中间里面也要有一个 basis。
对，但是如果 SAS basis 的话，其实你就不用再特地去找那个 open board，它的 intersection 就是其中一个，它就是其中一个，open。
所以是所有 basis intersection 出来的。
对，如果你用同一个 set 做出来的，用用 SAS basis 做，用 basis 做，这两个同一个 set 做出来的，SAS basis 做出来了会 finer than basis，对吧？
会比 basis 小，
不是小，
大了，有
容乃大。
有
表 U 对，没有错。
是 basis 与 basis 之间的 intersection。
对，可以，要开始了。 Okay, let's start. Okay, so this proof is an example of proof is you can use very logical definition to prove it, but actually there's a deep diagrammatic meaning, topology meaning, geometric meaning. Okay, so let's do a very nerd proof. Let's do a nerd proof first. Okay, so let's say what's the nerd proof? Nerd proof is you like a machine, you just throw a definition out, throw, and then you prove it. Right, later we're gonna draw it. What does it mean? So if I only if right, there are two directions to prove of. Okay, let's do left to right. Okay, suppose A is closed in Y. Okay, and then you want to show that there exists a closed set in C such that you can write A as a intersection. But there's nothing really much you can work with. Okay, so just throw the closed definition out. So what's the closed definition? Then the complement of A is open. In Y in particular. Okay, it's in particular open in Y. But open in Y means what? This is a subspace topology. So meaning what? So there exists an open U in X such that Y minus A equals to U intercept Y. Now is the problem already. How to find C closed such that A equals to C intersection Y. Okay, so this information here doesn't tell you about A, but it tells you about complement of A. Somehow you need to use this condition to find the C. Okay, I let you think a little bit. Don't just think you must, in this class, what do you need to do? Start with D. You must draw it. Draw on your paper. Quickly, quick draw, draw. Draw it. Draw it. Oh, 这个是 X。what's your Y? Let's draw Y. Draw A first. Should we draw Y first? Draw Y first because Y is a subspace. Y is a subspace. And then you have some A lah. A is closed in Y, right? A must be at least. So let's say A is. So Y take away A. Maybe A is somewhere like this. So Y take away A. Where is it? Y take away S. So how should this U look like? Doesn't cover A. Okay, but pass by the, let's say, the boundary. Something like that. Okay. So from here, you need to find the closed set C. Such that C intercept Y is A. What's closed there? You need to write A as some closed set inside X that intercept Y to get this part. The idea, what C you need to take? Everything outside U. Because everything outside U is perfectly a good closed set, first of all, because U is open. But now what do you need to argue then? You need to argue that, so this is closed, perfectly good closed set here. You need to check also, A is actually X intercept U, sorry, X take away U intercept Y. True or not? Is it true? How to check? How to check this? You need to use set theory to check out. Okay, so how to check? So if you is a point in A, you must be in the complement of U and in Y. True or not? For sure, A is in Y, right? Because it's a subset. But from this picture here, at least from this argument here, you can see that X take away Y. Sorry, element in A should be in a complement of Y, U. Okay? And then you show the other direction. Yeah. Okay. Okay. Question 了吗？有题吗？还是我们可以用一些 set 的definition 把它写下来嘛 ？Let's see. So can we do this? Okay, so let's do some extra stuff here. Maybe we can consider y minus a equals to y minus the whole thing. Okay, let's use the set theory stuff to prove it. This is true if and only if y minus a equals to y take away x take away u union of y take away y. Correct? And then this is equals to what? X take away x, y take away x, take away u is what? What is y take away x, take away u? The claim is that this one should be u intercept y. I mean, y take away u, y is empty lah. Right? So the claim is if you take y, so if you take y, right? Take y here, take away x, take away u. And can you imagine or not? So if you take y here, okay, take away x, take away u. So you are just taking away this part. Take away the a here. What do you left with? It's just this u here intersect with y. This part here. So can we use set theory again? Y take away something, take away something. Is there a convenient way to show this? Anyone know? Instead of showing by element. Okay. Well, should I work out something? So this is equals to y take away. How should we think about complement using intersection? It is x intersect with union of u of c, right? Okay. And then y take away x union what? Y take away uc. Okay, but y 把 x 拿走是什么意思啊？全部都就会拿完掉。It's again empty set. Okay, you left with what? Y intersect with u c c. Hey, 好了，我可以去考试了。OK 吗？有 question 了？Ask a question. So what we do here is just we write the complement as an intersection. Correct or not? What is x take away u? The UC. But how do you get UC? One way to get UC is just take a whole space intersect UC. Okay, no? So this is the trick we use here. Okay, makes sense. Maybe I draw some empty set for you first. So here empty. Okay. Okay. Got question? Got question? 哎，got question please ask 啊！不要以为我讲很简单就很简单啊，世界上没有简单的东西哦，没有白色午餐。Okay, if you have no problem, just feel free to ask. Got question? Okay, my job is make sure you understand. My job is not to confuse you. Maybe sometime I'll try to confuse you. Okay. The point, the point to confuse you is to make sure you understand. It's not the point of confusing you is not to confuse you. It's to make sure that you understand. Okay. Yeah. Okay. Next. Actually, the other direction is harder than this one. Actually, this one is already easier one already. Okay. So suppose A is as a intersection of closed set with the subspace. Okay. There are two things to show, right? There are two things to show. Subset is quite obvious. Is it obvious? It's obvious, right? Because it's intersection. Okay, then we need to show the other one. So first, we see that A is a subset of Y. Pretty obvious. Because it's an intersection with Y. It's a set that intersects with Y. So next, we're going to show A is actually closed in Y. Okay, that is what? What's closed in Y means? Okay, check again. Ivan, what does A is closed in Y mean? AC, what's AC in Y? Y minus A. Okay, it's opened. Y or equivalently, okay, subspace topology, subspace open topology that exists at open U, okay, X, such that Y minus A equals to U intersect Y. Okay, so now you're gonna find open set now. Just now we're finding closed set. Now we find open set. Okay, how to find this? Got picture again. One picture. What's the picture you have now? You draw your X again. And then you draw your Y again. Let's see, let's pull our A like this again. So now you write it as A equals to C intercept Y. Okay, so your C should like include this boundary corner, for example. So what's the open guy you can take here? X minus C can try. We try first because complement of closed set is open, right? So let's try the obvious one. Okay, in mathematics, you need to start with the obvious one first. Try the obvious one. Okay, if fail, then adjust again. This is what we do in real maths. So simply take X minus C, which is obviously open. So now we need to check whether Y minus A is equals to X minus C intersect Y. Is it true? Is it true? Again, what do we know about A as an intersection? We just know about this A equals to C intersect Y. Okay, so let's turn this equality to some A equal to some intersection. So if you take complement of both sides, becomes what? A equals to Y, take away the intersection. Equals to what? Y, take away X minus C, union with Y, take away Y. Okay, play the same game 来，招生帮我做完它。Y take away 哎，不是抄一样东西。OK，好，可以继续。Intersect x minus e complement。OK，还要吗？嗯哼，又超过。应该是 complement。OK，好，然后怎样办？嗯嗯嗯嗯嗯。S complement 是什么东西啊？S complement 是 empty 哈。OK，and then y intersect C 哦，this is how we started with 哦。OK，哎，你看，我们现在在做一个实验呢。我刚刚教的步骤都不是这样的，结果他跑来另外一个步骤还是对的，你懂什么意思吗？In mathematics, there is no fixed way as long as you are using the right method。才下一秒罢了，他就用不一样的东西了。如果跟着我的方法，我不是这样，不是我应该是先把这个 S 减 C 变成 intersection 先嘛。But the key point here is as long as you know how to make the complement into intersection of some complement, then that's fine. No matter which direction you want to use. Okay. Okay. Makes sense? Okay. So good. So we prove it. So hence A is closed in Y. That's decided. Okay. Next. Okay, next. We'll go pretty fast. Let's go pretty fast. We will repeat what we do in metric spaces. So let's given a subset A inside your topological space. Okay. The interior int A. Okay. How do we define interior of A? In this case here, we will define it as the union. Okay, union of all open set contained in A. Okay, all the open set contained in A. Okay, sometimes we say open set in A also. Okay, so don't be confused. Okay, so don't be confused. Just now we say open in A. Now we say open set in A. So don't be confused. So the open set here is just some open set in X. Or sometimes we say open subset. Okay, so be careful. Okay, we are not talking about subspace topology here. Where this U alpha is open. Okay, for O alpha. How about closure? Okay, how about closure? So what we're going to define for closure is for A bar. Okay, is defined as the intersection, okay, of all closed set containing A. So A bar is equal to the intersection of all C alpha where so closed C alpha will contain A for all alpha. Okay, so it might not be clear to you why we do this. Okay, later we will show a bunch of property here. Okay, maybe it's not clear to you why. 为什么啊？为什么我要这样做啊？为什么？有些人就是很欠，我也很欠。为什么要这样做？凭什么这样做？ Okay, but we will show a bunch of property that justify, okay, the word closure interior here. But there's one very nice observation to make here. What do you see? We define using union and intersection. Again, set theory. Okay, and then define using what? Open set and closed set. So that's why topology is important. Okay. So we put union on open set, put intersection on closed set. Makes sense, right? Correct or not? Because just now we say is what? Arbitrary union of open set is open. Arbitrary intersection of closed set is closed. So we no need to care about 拿了过后还不是是不是 open， 拿了过后是不是 close， 不用 care arbitrary 啊。Check out, yeah, check. So this is the property that we cover in this open and close. Okay, being open and being closed. Okay. Okay, so proposition. Let's see what we can do with these things. So first thing is the interior of A must live inside A, and then A live inside A closure. Okay, match our intuition here. Okay, 里面的东西一定要在里面，包起来的东西一定是包含所有东西。他讲废话呢？啊？我的扣什么？什么是你？介绍自己。Okay, yeah, so it's the next line. So if A is open, actually you have the other direction. A equals to in A. Okay, if A is closed, then actually A is just the A closure. Matches up what we want. Okay, if we define it. So let's show this. Proof. Okay, so nothing much to work with. We just need to start with definition. Okay. So what do we do here? Okay. So what is in A? What is in A here? So let's put 1, 2, 3 here. In A by definition is what? Good arbitrary union of all open set. But all open set should live in A, right? So the union also live in A. Very straightforward. Okay, how about the other direction? Again, you use definition of A bar. What is A bar? Arbitrary intersection of C alpha. But all these C alpha contain A. So A should live in all of them by definition. 每个人都有 A 吗？对，每个人都有 A， 每个人都有 A， 应该是全部学生最喜欢听到的一句话。每个人都有 A 啊，对不对？每个人都有 A。没有，马来西亚人对 A 是很敏感的，你知道吗？我是吧？我父母是每次这样的，要拿 A 啊，考 A， 考 A， 考 A。新加坡人的 ，OK，I don't know。Okay. How about if A is open, then A equals to in A. We just left with another direction. But if A is open, what does it mean? In A is union of all open set. Particular A is one of the open set. A is already one of the open set. So A is inside your union. Correct or not? So you get the both direction. So not that. Not that what? In A can be written as union of U alpha union and A. Obviously is equal to A. Okay. Third, if A is closed, what does it mean? A is also one of the C alpha. Is also one of the C alpha. But every C alpha contains A. You take the intersection, you will get A. Okay, so if you take A bar is equal to intersection or C alpha intersect with A, everything has A is equal to A. Okay. So it's very convenient. There's no limit point whatsoever here. Just care about closure. Okay, let's put some remark here, some very important remark here. So remark, if A is a subset of Y, the closure of A in Y and the closure of A in X is generally different. Okay, they are generally different. Okay, close in a subspace and close in the whole space could be different. So what do we do is we were gonna reserve the notation. So whenever we write the notation A bar, we were referring to the one with the original space. Okay, not the subspace. And we try not to use the same notation. Okay, maybe I give you an example. Let's give you an example. So for example, what's the closure of this half open interval here? What's the closure of this guy? You need to put your one back. Okay, but what's the closure of this half open interval in itself as a subspace? It's just itself. Okay, why? We could argue that because it is the only closed set in this subspace such that 0, 1, the half open interval 0, 1 minus 0, 1 is equals to empty, which we can write it as a intersection with the open set in X. Okay, so we claim that this complement is open. Okay. Yeah. Okay. So how are we going to talk about closure of a subset in a subspace topology? So now we're going to talk about closure in a subspace topology. So let's put a theorem here. So let Y be a subspace of X and A be a subset of Y. What's the closure? Okay, closure of A in Y. Okay, it's quite obvious also. What do is you take the closure in X first and then just intersect with Y. Okay, so if you look at the previous example also like that, you take the closure in R first, intersect with Y. So you get back your Y. Okay. Okay. Good here. Time is it? 32. Okay. Maybe I left this proof for you to try. Okay. So this proof is we will do some more interesting one. Okay, so you just need to show the usual set equality being closed by using the our intersection of closed set definition. Okay. Right. So sometimes the definition of closure of set, right? The thing the collection of closed set could be too big. So we try to use the closure of a set using open set to describe it. Okay, in particular, we can use basis element to describe a closure. Okay, we can use open set to describe closure also. Just now we define closure using closed set, right? Okay, so now we try to use open set to describe closure. So before doing that, we're going to define this. We say that a set A intersect or sometimes we say meet lah. Okay, you meet intercept or meet a set V if the intersection is not empty. Okay, we'll say that a set A intercept or meet set B if the intersection is not empty. Okay, so we're going to use this language to prove something. So let's take some subset, just subset, subspace, not subspace, just subset. Okay, so we'll say that X live inside the intersection of all the closed set containing A if and only if every open set U containing X will intersect A. Okay, think about this. If you live inside all the closed set, meaning what? All the open set that contain X must intersect A. Okay. Or cannot. There's some room to play here. A bar is what? Intersection of all the closed set containing A. Potentially, this intersection could be larger a bit than A. Okay, man? I just contain A is enough, ma. But if you build an open ball around there, this second condition here tells you that that open ball must intersect A. If X don't live in A, there's some other point live in A inside the ball. Okay, very close to the definition of the limit point we had last time. Exactly the definition that we had for the limit point. Okay, no? The limit point doesn't need to be inside your set, but every open ball around that point must contain a member of. So this part is a limit point definition actually. Okay. Next, either limit point, either is an isolated point. Next, suppose that the topology or tau is generated by a basis. Okay, suppose that it's generated by basis. Then X is in A bar if and only if every basis element B containing X intersect A. Okay, so what's the difference between statement A and statement B? Instead of checking arbitrary open set, right, you just need to check on basis element. Okay, basis element is enough to check already. Does it make sense? Right, so this shows another nice thing about basis elements. Okay, it's a fundamental open set that you need to build your topology. Okay, I think we're going to show this. This is pretty important stuff. This will link. So you should imagine the statement A. When we define A bar, there's nothing to do with limit point. Now we're going to pull the idea of limit point into it now. Where there's nothing to do closed set, just intersection of closed set. Purely set theory. Purely set theory. Okay, but now we're going to pull this idea of limit point. Okay, so instead of doing that, we're not going to do that straight away. So we will prove that the contrapositive of the statement. So S is not inside A bar if and only if there exists an open set U containing X that does not intersect A. Okay, so this is a proof technique. Because if imagine if you're going to prove statement A, you need to show it for every open set. But if you take the contrapositive, you just need to find one open set. You can take the negation. So let's try. This is easier. So let's do one direction, left to right. So if X is not in A bar, what do you do? Okay, I think it makes sense. I think it makes sense. Let's see, what am I doing here? Okay, so let's suppose S is not in A bar first. So if X is not in A bar, okay, you want to follow your idea? So let's follow your idea. Then X is in A bar complement. Then what does it mean by A bar complement here? So we can write it down, right? Just now we define what is A bar, right? It's just the intersection of all the C alpha such that C alpha contain A. Then you have to keep working out. Huh? So this one, you write it as C alpha union, yeah, right? Union of alpha of C alpha C. Okay. What can you do here? Don't forget your goal. What's your goal? 要做一做，忘记自己要做什么。What are you trying to do? You have to find an open set such that contains X first, such that it doesn't intersect A. So what's the U you can take here then? A complement. A is A close. There's an obvious close set here, right? A closure. Okay, so let's bracket this first. I'm not sure using this or not. So if you consider A closure, complement of A closure, take U to be the complement of F closure. Obviously, this set here will contain X. So the question is, what is U intersect then? Which is equal to what? X minus A bar intersect with A. Huh? Which is what? A bar C intersect with A. Huh? Yeah, but 要继续做吗？还是看得到了？看到了，讲看了，赵正。眼睛，喂 ，by inspection，讲看到，好，继续做嘛。啊，可以继续啊，怎么样？啊？What? Doesn't? Why? Oh, because why? Oh, sure. But we want to show that this intersection is empty, not just about X. You want to show that this intersection is actually empty. Okay, you just show that one thing is not in there. But why is it empty here? So if you do the calculation we did just now, right, it's a union of alpha C alpha C. Sorry, C alpha C, yeah, C alpha C intersection with A, which is what? Union of alpha of C alpha C intersect with A. But what is C complement of C alpha? C alpha contain A. Complement of C alpha shouldn't contain A. So there's nothing in A in C alpha C, so the intersection is empty. Okay. So this part is empty because C alpha C doesn't contain. Okay, as A is contained in C alpha. Okay. Okay, how about the other direction? The other direction. Suppose U is an open set containing X that does not intersect A. Okay. So you want to show that, what we want to show? We want to show that our goal is to show that X is not inside A. Okay. So what is A bar? You need to start thinking from A bar. A bar is a intersection of C alpha. Okay, so you need to play around with the closed set there. Okay, can you create a closed set that doesn't? What do you need to do? Well, I mean, so let's try some obvious thing. So if you have an open set, right, obviously you can build a closed set. Okay, just take X minus U is closed. But not that this is a closed set that contains A. The closed set that contains A. Why? Because U doesn't have A. The complement must contain A. Okay. Okay, so meaning this is one of the closed set that you take to intersect inside of A bar. Huh? Or what? This term is one of the intersection term. But this X minus U shouldn't contain X. X minus U is one of C alpha. But this set already not containing X. Okay? Okay. So we are done. Okay, so by definition of A bar, we should have X minus union containing A bar. Okay, so right intersection. Because A alpha is even more intersection. But A alpha should live inside X union. But X is already outside X minus U. Okay. Okay, I suggest you draw it. Please draw it. Okay, try and draw it. So hence X is not in X minus U. Okay. Okay now. Cool. Okay, so for the basis one, I leave it for you to prove. Okay, similar thing you need to do here. Okay, but the point here is you don't need to check on all open set anymore. You just need to check on basis element. Okay. Okay, next. Okay, next we're going to define something called the. Yeah. Okay, one more time. Hey, can let me finish at 6 o'clock now? We're a bit behind. No, sorry, 5 o'clock, 5 o'clock, sorry, 5 o'clock. Not 6 o'clock. 6 o'clock is too much. Okay, 5 o'clock, sorry, 5 o'clock. Okay. You need to leave earlier. Okay. I pardon you. Okay, let's U is a subset is in this topology. If U is an open set containing X, okay, then we will say that U is an open neighborhood. Sometimes if you see the literature, it just say neighborhood. Okay, but we will make it clear that it is an open neighborhood. Okay, so this neighborhood is pretty open. Okay. So Moncrief used neighborhood to be precise, but Richmond used open neighborhood. So why we pick open neighborhood here? Because so that we are consistent with the neighborhood we talk about in metric space. Okay, so if we phrase it in this way, then the theorem just now will be rephrased as such. So if you are a point inside the closure, if and only if every open neighborhood intersect X. Sorry, intersect A, not X, because we are talking about A bar. Okay, so we call an open set that containing X as the open neighborhood of X. 合理吗 ？OK， 这就是被一个 open set 包住。OK， For example, should we give some examples here? Some examples. Well, should we give examples? Okay, nothing much. Never mind. Let's keep this. So let's give the example of limit point now. So motivated by this, we will define that a point x is a limit point, cluster point, cluster. So form a group or accumulation point. So these few words there will be used in various literature. The older you can find, the more cluster point, accumulation point you will see. For the modern one, I think you just see limit point. Okay, so it's a limit point if every opened neighborhood of X intersect A in some open set in some point other than X itself. Okay, so you see the logic of introducing this limit point is kind of opposite when we define limit point in the metric space. When we in metric space, we define limit point first, and then we talk about closure. What is closure? Closure is just the set union with the limit point. Okay, so we kind of do the opposite logic here. Okay, so this is another nice thing about Maxwell. Okay, we define something, and it turns to work out the way that we want it to be. Okay, based on the example that we know before. Okay, when we define closure, there's nothing about limit point one. We just talk about intersection of closure. Okay, and then we show that it is true if and only if it satisfies this limit point property. Okay, and then we define that that point is a limit point if it satisfies this condition here. Okay. Okay, so skip the example first. Next time we can talk about it. But you can see that what's this theorem here? This theorem is we will prove that A bar equals to A union A prime, where A prime is all the limit point of A. Let's prove this and then we will finish off today. So we recover the theorem in metric space. Okay, we recover. So on the left side is just intersection of closed set. Okay, on the right side is something about open neighborhood, open set, topology. Okay, open topology. Okay, let's prove this and then we will finish off today. Okay, again, we will do the nerd thing, very nerd. Just use definition to show. So let's go from right to left first. Okay, A union A prime in A bar. Okay, so any inclusion is obvious here or not? Which inclusion is obvious? You want to show everything on the union is in the A bar, right? So you need to show that X in A is in A bar, S in A prime is also in A bar. Okay, which X is easier? By definition, A is already living inside A bar because A bar, every closed set will contain A. Okay, how about the second case? If X in A prime, what does it mean? By definition of limit point, then every neighborhood of X will intercept A, and then haven't finished, in some point other than X itself. In particular, what does it mean? This means that in particular, they intersect A. But what is this? This is the theorem that we prove, right? Okay, if what's the theorem? If every open neighborhood of X intersect A, then X is in A bar. Okay, so by the theorem before, X is in A bar. Okay, so this is a very good example that in Max, what we do, 我们只是把一个 property 命名嘛，给名字嘛，给它新的名字嘛，转来转去都是同一个东西，我给它新名字。OK 了。OK， 其实是我们做过的东西，把天人比，我只是给它一个名字叫 limit point 嘛。OK， so we give new names， 对吗 ？New names, do you agree that new names is more convenient? Instead of talking about every blah, 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 we just tell you a limit point. It's a limit point. 不是比较，对吗 ？This is what mathematics is doing. We give new name to a long property. 就是它我这个。And I think okay, and then I think I need to justify a bit. So maybe this is one thing that make mathematics hard also, because you need to know what every word means. 每一个字都藏了很多东西在里面，所以就很难，因为每一个字你都要知道是什么意思，每个字里面又有很多意思。I think this is one thing that make mathematics pretty hard. Okay, every definition contains a lot of property. Okay, next the other direction. Okay, prove 完这个我们就回家。Okay, so let's do this. So now suppose X is in A bar, and S is in A bar. Okay. So, well, you want to show that X is either in A or A prime here. Okay. So if X is already in A, then we are done. So either in A, either not in A. You can only be in one of the cases. Okay, if it is in A, it's done. Otherwise, assume X is not in A. Okay. Assume X is not in A. Since X is in A bar, and what we know that every neighborhood U of X intersect A. So, meaning what? Meaning that as X is not in A, what else should be in A? Then the set U must contain another point. Okay? Another point in A other than X. But this is while we precisely define A prime to be the limit point to be. Okay, so it will live. So X will live inside the set of limit point. Okay, so a corollary from here is we recover the metric space property. That is a subset of a topological space is closed if and only if it contains all its limit point. Okay, we recover what we had for our metric space. Okay or not? Any question? Okay, we recover, we work backward. In metric space, we use limit point, define closure. And then now we go from closure back to limit point. B 在闭环关在一起了。OK， 数学有一个很美的点，就是你从左边打它，从右边打它，它都是一样的。从哪一边都行啊。Everywhere you move, the solution is the same. 如果你左边做一下，右边做一下不一样啊，就有问题。 啊，肯定有问题的，这数学。反正数学好玩的地方就是你怎样打怎样走，它都是一样。啊什么？不是你什么不是 ？OK，呀，对，那个OK，OK 吗？Yeah。Okay, next part we will go to Hausdorff space and then continuous function. Hopefully we can finish by next Wednesday so that you can finish every question inside your assignment. But you can start doing some of them. Okay. Okay, see you next week.